Hi, calculus class. Today we're going to attempt to learn how to find volume using what's called the disk method, and we're only going to start by revolving around either the x or the y-axis. The process for setting up your integrals is going to be the exact same. The only difference is whether you use the variables or end functions with x in them or with y in them. And that's going to be very similar to what we've been doing with the area and the volumes using known cross sections the last few days. Okay, so we're going to talk a lot about setup and how we figure these things out, and do one example before I let you try some on your homework. And then, as always, I'll be available via email or Remind 101, whatever it happens to be. You can, whatever question you happen to have, you can certainly contact me, and I will get back to you as soon as I possibly can. So when we find volume, we're going to start by looking at a representative rectangle, okay? And that representative rectangle is going to be revolved around an axis. That means it's going to be spun around a line, okay? Imagine if we took this rectangle that's here, right there, and we spun it around our axis of revolution. Okay, we always draw these strange little arrows in there to show that we're going to spin it around. You can imagine, hopefully, that if you spin that rectangle, you are going to get a disc shape, which is really a cylinder, but we call them discs in calculus for some reason. We get a shape that's just a cylinder, and we all know how to find volume of a cylinder is this fairly easy formula from geometry, the pi r squared h normally, but since they're sideways, our height is kind of like our width. All right, the idea is the same as when we talked about cross sections. If you know the area of the cross section, in this case our cross section is going to be a circle. If you can integrate an area formula, you can find volume. So the volume is going to be very similar to this volume of a cylinder formula, except you're not going to see a width in there. You're not going to see that height, because the idea is that we make our discs so skinny, so flat, that their width is not even relevant, really, and we just integrate the area of one circle and we find volume that way. So we'll practice this for a couple days, and then we'll move into the washer method, which is even more exciting. I'm really excited to do that. It's so much fun. Okay, so the volume of a disc, like we just talked about, is the area and the width, and you are not going to see the width, okay, when we actually get to the integral formula. So here's kind of the best diagram I could find to represent what's going on. So originally we're going to start with this function over here. You can see that there's a kind of funnel shaped sort of graph going on there, and we have region R, the light blue shaded region, and we're going to spin that, we're going to rotate it around the axis of revolution. Okay, and when we spin this light blue region, you can ignore the representative rectangle for right now, we get this three-dimensional funnel shape. It doesn't have a hole in it, so it's like a filled-in funnel, but that's kind of the shape that we're talking about. And for us to estimate volume, we could start cutting it up into these little stacked discs, right? And we could add up all of the discs, and if we wanted a better representation, we'd maybe do twice as many discs and all of those types of things. And as soon as we let the number of discs go to infinity, then we're talking about a definite integral. And that's why this delta x of the representative rectangle doesn't even matter, because we make them so narrow that there's really no width to talk about. Okay, so on the next slide here, we're going to see what those formulas actually look like. This is called the disk method. If you want to search for other videos that might explain things slightly differently, totally cool. Search something about the disk method and you will find any sorts of videos out there. I'm sure there are a ton. But the formula setup is slightly different, like it is depending on whether we're horizontal or vertical. So if we're going to rotate around a horizontal axis of revolution, today that's going to be just the x-axis. So we're either doing x-axis or y-axis today. Anytime it says horizontal axis of revolution, we're rotating around the x-axis, and we have our functions in terms of x. That r of x is representing the radius of the disk we're looking at. You can kind of think of it as a cross section after revolution. So it is going to be a full circle. All right. If we rotate around a vertical axis of revolution, always look for these arrows in any diagrams that are given to you. Or if you're drawing your own diagram, put those arrows in there just so we know where the axis of revolution is. If we do it across the vertical axis, the y-axis today, all of our functions will be in terms of y, just like they have been the last few days. Okay, so notice because pi r squared is the area of a circle, we have the radius squared inside. We have the radius squared inside there, and pi is just a constant, so we pull it out front just for ease of calculations. All right. Okay, here's an example. Honestly, the hardest part of these is visualizing what the solid is, but when it's just around the x or the y-axis, they're not too terrible to figure out. If you have any troubles with that, definitely let me know. I'll do my best to guide you on what these things look like. Always start by sketching a graph of your function you're given. It does help visualize, and I always draw in a representative rectangle as well. Super important. It just helps us visualize what's going on. So here we have a solid formed by revolving the region bounded by this graph. F of x is root sine x, and the x-axis around or about the x-axis. So I just took a copy of the picture from the book, and we have our region. When we rotate it, here's the three-dimensional object down here. It kind of looks like a football or an egg or something like that. So we can imagine that if we start slicing that perpendicular to the x-axis, that we are going to get a whole bunch of circles. So when we set up volume, we need, remember, our equation is going to be pi times the integral from a to b of our radius squared. Okay, and this one is in terms of x because we're revolving around that x-axis. Okay, so let's talk about what our radius is. Our radius is not a given number, it's a function, as you have seen with the cross sections. Like our radius there is whatever that number is. Over here we have something maybe closer to 1. Here we have a radius of almost 0. So we have to represent that. And anywhere along here, wherever you draw your representative rectangle, we have this function that represents our radius. So our radius is going to be the square root of sine x. That's our function, our radius that we get to plug into our volume equation over here. So to figure out volume, we're going to have pi times the integral a to b. Those are our limits of integration, and there are intersection points. So we're starting down here at 0, and we're ending here at pi. So my integral is going to go from 0 to pi. And we said our radius was the square root of sine x dx, but I gotta square it because it's pi r squared. Okay, this is a fairly easy integral to do on our own, so let's just practice that. The square root of sine x squared is just sine x. And you can all integrate sine x very easily. That integral is negative cosine x, evaluated from 0 to pi. I'm just leaving this pi hang out front for a while. Negative cosine pi minus negative, so plus cosine of 0. Negative cosine pi is 1, because cosine pi is negative 1, and cosine of 0 is 1. So we get a volume of 2 pi in this case. A volume of 2 pi, and that one actually turned out pretty nice. Some of them will not be as nice. Leave them in terms of pi by all means. You can, if it's a messy integral that you're trying to do, of course you know how to do that on your calculator as well. This was just one example. Let me know if you need more. I will happily post more and help you along the way. See Power School for your assignment.